All right, let's go ahead and start lesson 3.
What is the amount?
Now what we're going to do is we're going to take what we learned about the CART system, and we're going to look at other types of systems now. And arguably, worksheet 2 is probably one of the more difficult ones of the year. You may think you know what's going on, but then you'll get there and you'll be like, oh, my answers are very much different than everybody. So what we're going to start with is the basic ideas. And I would start with this. I would have this on a note card or at the top of every single worksheet that I did. Here's the 4 principles that you need to solve these problems. I went over 3 of them yesterday. Right? Number 1, make sure you get this down. This is to help you when you get stuck. Number 1, start with a force diagram, all right, and draw to proportion. Draw proportion based upon the motion. That motion component is huge. If it's constant velocity, they all cancel out. If they end up that force is 0. If it's acceleration, it means one's going to be bigger than the other. Okay, so the next thing is force net. You have 2 different versions of force net. Force net is mathematical sum, is the mathematical sum of all the forces. Alright, so you're going to look at how they all are in relation to each other. Step 3, or the third thing that you need to know, that you might need to know, is that force net, you're going to mass times acceleration, where m is the mass of system. And the last principle is one from last unit, which is force gravity is equal to m times 10 newtons per kilogram. Yeah, I'd have this at the top on a note card of every single time I started one of these problems. Alright, so that you can solve pretty much all problems with that, with those basic principles. Alright, so a physics clown, the mass of 75 kilograms, is in an elevator standing on a bathroom scale. It's a clown because why would anybody ever do this? Starting from rest, the elevator accelerates downward 3 meters per second for 2 seconds, and then continues at a constant speed. A, construct a force diagram for the clown. B, sketch velocity versus time. C, what's the scale reading during the acceleration, and how does this compare to the scale where the elevator is at rest? All right. So we'll go ahead and draw a force diagram for this clown. And then we'll do our knowns and unknowns. So let me scroll this up. So this thing is going, this elevator is going to start off slow. Except they want me to choose colors. Choose blue. Is that blue?
Blue.
Okay. There we go, it's purple. I'm not going to do the colors.
Why is your thing so uncalibrated?
I don't know.
There's no point.
Because I'm uncalibrated. Alright, so this thing's going to accelerate down. My system is the clown. You'll see why I do the system as the clown in a minute. It's a whole lot easier to do it this way. Because all I have to think about is what's happening with him. Alright, now, what forces are acting on this clown? Force gravity. Force gravity on clown. by earth. What else?
Force normal.
The force normal. Now, which is going to be bigger, the force gravity or force normal?
Force gravity.
Force gravity, why?
Because it's accelerating greater
Is
force.
it is accelerating down? We're basing it on the motion. That's this first one. Based upon the motion, we're drawing to the proportion. So I don't know how big this is. I just know that the force gravity needs to be drawn bigger. Force normal on cloud by what? Scale. And I'll show you this demo. I don't have it set up tomorrow. But have I talked about what the scales actually measure?
Yeah, the force. What scale are you talking about?
It's the force that's pushing you up. That's why when you jump on a scale, it goes more than what you actually weigh. And I'll show you that. I have a force plate where you can watch. I have a scale that will show. I don't have time to show it today, but I'll show it. So when it's asking for the scale reading, it's actually asking for this value right here. All right, now let's do our knowns and unknowns in this problem. Okay, so what's the 75 kilograms? Where does that fit? So mass is 75 kilograms. This is actually easier than our cart systems because there's only one piece of the system. Okay, what else do we have? So the 3 meters per second squared, what's that?
Acceleration.
So acceleration is 3. Now, we need to keep direction in mind. So if we call up positive and down negative, which way is it accelerating?
-3 meters per
It's going to actually be -3 meters per second squared. And then what are we trying to find? Scale reading, right? So that's going to be our force normal. Notice, I have yet to try to solve this problem. I'm not even there yet. I don't want to be there yet. I'm not going there yet. So the next question it asks is, what does the velocity versus time graph look like? And again, that's just a directional thing. He's speeding up in the negative direction, so he's got a negative slope. I just determined that there. All right. I am now going to attempt to solve this problem. Oh man. There's one other piece of information we can put on here. Do we know either of these values right here? Can we find either of these values?
Yes.
Jeff, how do you find it?
By knowing the mass of the corner.
Mass of the compass. So we can say this is m times 10. We're using this principle right here, principle number 4. So that's going to be 75 kilograms times 10 newtons per kilogram, giving us 750 newtons. So the force gravity then is 750. We'll call it a negative 750 because it's going down. Okay, now let's try to solve this problem. How can we come up with the value of force normal? You got to use these two principles right here. Any ideas? Gage, you got a shot? Take a shot.
We take the mass of the system, which is 75 kilograms, times our -3 meters per second squared to get the force net.
All right, so let's go ahead and do that. We can do that. We can find force net because we know our mass, right? And we know acceleration. Using that equation there, that's 75 times -3. So that's going to give us 225, negative 225 newtons. There. Okay, Gage. Now what? How do I get the force normal?
You would subtract this -750 newtons.
Very good. Yeah, Gage, you got this right on the money. So what you do now is you take this principle here, the mathematical sum, which is force net is equal to force normal plus force gravity. Do we know force net? Yep. Do we know force gravity? Yep. So then we can find our force normal. Very good. So now let's just go ahead and do it. Let's go ahead and execute our plan. So that's negative 225. It's force normal. Plus negative 750 or minus 750. You don't have to. You can skip that step. So we take negative 225 plus 750. Add both sides. 750 to both sides. So what is it?
525.
525 newtons. Now let's do a reality check. This should be smaller than this. Is this value smaller?
Yes.
Yes. That answer is again going to make sense. Okay, that's a good answer. Okay, and again, you can look and see whether or not your answers make sense. If your answer doesn't make sense, you probably did something wrong based on your drawing. That's actually why I like these problems. That's why I think it's easier than Newton's third law. Because in reality, you can always check. And then the third law we did last unit, you know what I'm saying? There was no basis for checking.